Hello everybody, my name is Pete Williams and I'm Senior Nutritionist with Green Plains Inc., a major ethanol producer out of Omaha in the United States. First of all, I'd like to thank Aquafeed for the opportunity to make this presentation. And today I'm going to talk to you about the production of a 60% sustainable vegetable protein product. We call it corn fermented protein, which is derived from the ethanol industry. Before we go any further, I'd like to tell you a little bit about Green Plains. Green Plains has got annual sales of over $1.9 billion and it processes over 10 million tons of corn annually. So what are we doing here? The bioethanol industry started with a co-product out of that industry called distillers' dried grains and solubles. At the time, this was a waste product. We're turning that waste product into a designed feed. Not only are we producing a high protein product, but we're producing a renewable fuel, we're producing corn oil and industrial alcohols. So we're turning that bioethanol industry into a biorefinery. That biorefinery will annually produce, by 2025, over 500,000 tons of high quality protein every year. So let's consider the running order for this presentation. I want to start by talking about what makes a commercially renewable alternative protein. Then I want to talk a little bit about corn and just how important corn is as a sustainable crop. Then we get on to talking about the product, corn fermented protein and its use in aquaculture diets, future strategies and a few conclusions. So what makes a commercially viable feed alternative protein? Well, you'll have to look at the size of the industry for a start. And we start with what's a critical volume to produce to get a new protein into the animal feed industry? Well, that volume is about 100,000 tons per annum. You've got to have a large volume to fill bins because of the scale of agricultural production. You've got to have resilience in the supply chain. When we first started producing corn fermented protein, we only had one plant. And agricultural producers were not keen to take on the product because there was no resilience in the supply chain. If the plant went down, they lost their product. You need redundancy in the supply chain. You need to have enough material there that when someone wants some more material, you can supply it. You've got to have your supply logistics. You've got to be able to produce a consistent product. In the animal feed industry, the one thing that an animal feed producer does not want to do is to change his formulation. So you've got to have consistency in the product that you produce. And to get them to use that product, you've got to have tried it, tested it, and proven it in livestock trials. The industry is looking for alternative proteins. The alternative protein business is worth about $2.5 billion annually, with a compound annual growth rate of 7.1%. That tells you that there is a need for alternative proteins. What are the top alternative proteins that are available for us at the moment? Well, you can go into new agronomy and canola meal, pulses, cottonseed, sunflower are relatively new crops that we could use for alternative protein. There's a lot of work going on with respect to fermentation technology, single cell proteins and brewers spent grains. And then finally, you've got what you might call discarded materials, processed animal proteins, and now there's this whole technology about insect protein using materials that we can't get currently into the feed chain as alternative proteins. But let's go back and look at the possibilities of producing new alternative crops for alternative proteins. So let's consider what it takes to get a new alternative agronomy in place to produce a new protein crop? Well, first of all, you've got to select your appropriate cultivars for the region in which you're going to grow the crop. Now again, coming back to corn, corn now has different cultivars for all the different geographic regions in the United States. To get an alternative crop to do that will take several years to develop the crop and to actually produce the elite varieties. You've got to have experience in the farmers to produce the new crop. They've also got to have the right equipment to produce the new crop. Again, that takes time, that takes money. You produce a new crop, you've got to know how to handle it and how to formulate with it. And if it's not right, regeneration can take several years. You need also policy and research to demonstrate how these new crops can be used in livestock production. All of this takes time, takes money. That favours the status quo. We have a crop, the number one crop in the United States, corn, and if we can use that with all the logistics in place, that all has been put behind this crop, then we have the opportunity to make corn into a multi-purpose crop. So let's look again at corn and just how sustainable a crop it is. We're breeding elite varieties for climate and geography. We've got genetic improvement, we've got disease resistance, pesticide resistance, drought resistance. We produce it in an industrial scale, and we're now using the corn stover, as a renewable natural gas and ethanol producer. We've got an agronomy that has been adapted to corn. Low or no till, double cropping, in-seeding and cover crops. We've also got the use of the corn kernel and its use in producing renewable fuels and, as I'll tell you, an alternative protein. Based on the Norwegian SINEF database, corn protein products are allotted greenhouse gas values 5 times lower than protein concentrates derived from soybean meal, and the land use change more than 100 times lower than protein concentrates derived from soybean meal. So if we can make corn into a protein crop, not just an energy crop, we make it into a multi-purpose crop that can compete in the protein market with soybean meal. So let's talk about corn fermented protein. Corn fermented protein is a vegetable protein product produced from corn. We can produce an alternative protein ranging from 52 up to 61% by the use of enzymes in the initial fermentation process. That fermentation process is a 60-hour fermentation at the start of the whole process. So we get the benefits of fermentation. I'll talk about that a little bit later on. The MSC process is a mechanical separation of fibre, fat and protein. It is a total mechanical process. There are no additional processing aids, no additional chemical processing aids. We've also got to the stage of being able to run the process without any antibiotics in the fermentation process. So we fit with the NAE, no antibiotics ever, production of feed for animals. We've got 8 plants in operation and 2 in construction. So we have resilience in our supply chain. When we look at products out of the bioethanol industry, one thing that we've never done is look at the production of yeast in the process. A large-scale bioethanol plant will produce over 14,000 tonnes of spent yeast annually. As nutritionists, we're well aware of the value of yeast in animal nutrition. Corn fermented protein contains, the 52% corn fermented protein contains approximately 24% spent yeast products in the dry matter. 20% of the protein in corn fermented protein is derived from yeast. So we get the benefits in animal production of the mannans, the glucans, and these benefits that can improve the health of the livestock when we use corn fermented protein in the diet. It makes the corn fermented protein into a functional protein. We get the benefits of the yeast. I alluded to the 60-hour fermentation at the start of the bioethanol process. There's a tremendous amount of research that has been carried out to identify the benefits of fermentation. It has been shown using holo analysis that fermented feeds have improved protein digestibility, there's an increased number of small peptides, there's increased energy digestibility, and the meta-analysis has shown improved nutritional value, bioavailability, weight gain, and food conversion rate. So that 60-hour fermentation is a tremendous opportunity for us to use alternative enzymes, and one of those is phytase, to improve the availability of nutrients in this bioethanol process. I talked about the need to demonstrate the efficacy and the value of products when we take new products to nutritionists. We've carried out, it says here 30 trials, we've actually carried out over 40 trials in different research institutes worldwide to demonstrate the value of corn fermented protein. The first point, corn fermented protein is a highly consistent product. Now, products out of the bioethanol industry have got a bit of a reputation of being variable, and that's because of the process and how components at the end of the process are put together. When we go back into the process and we use mechanical separation to produce corn fermented protein, we can take out all that variability. We've carried out ileal digestibility in cecectomized cockerels with Carl Parsons at the University of Illinois. We've done that over the last 10 years, and we've taken product from different plants at different periods of time. The average ileal digestibility of corn fermented protein in cecectomized cockerels is 89%. But the important point is there is less than 2% coefficient of variation in that product. We have a highly consistent product in terms of in vivo availability of amino acids. We're talking about the use of this product in aquaculture. We've recently carried out trials with Atlantic salmon to look at the apparent digestibility coefficient in Atlantic salmon. This was by the modified Guelph system, where we're collecting feces, we're not actually stripping the fish. The apparent digestibility of protein in Atlantic salmon is 95%. So we have a highly digestible, highly consistent product produced by this process. When we're producing proteins, it is important that when we dry the product, we use gentle drying. The presence of sugars plus high temperature and moisture will produce Maillard reactions. So it is very important that the drying technology that we use does not destroy our protein. Standard drying in the bioethanol industry is by a rotary dryer, where there's contact with the hot surfaces. And the coloration that we get of distillers' dry grains and solubles is often due to the production of Maillard products. We don't use rotary drying when we produce corn fermented protein. We use a ring dryer. We've looked at the availability of lysine from the ring dried product, and our availability of lysine is approximately 97%. So we're not losing any lysine from the production of Maillard reactions in these products. We have a high quality protein, we dry it gently using ring drying. We've carried out over 40 in vivo trials with corn fermented protein as a supplement for different species. We've replaced fish meal and soy isolates in aquaculture, replaced soybean meal in feed for broilers, replaced soy isolates in diets for turkeys, used it in pet formulations, as a protein supplement for starter pigs. And actually there are characteristics of the protein that make it a rumen undegradable protein for dairy cows. It's the benefits of the gentle drying, the benign protein, and our targets for the use of this product are particularly in the diets for neonates, where the use of a benign protein, lack of anti-nutritional factors, starts to be of real benefit. Because we've got a benign protein, no anti-nutritional factors in the protein, we've got yeast as a functional component in the protein, we feel that this protein is of value in aquaculture. We've completed trials in trout, salmon, tilapia, shrimp and carp. And without exception, we've had equivalent or better performance to the controls when the controls have had a range of different proteins, either fish meal, soya protein concentrates. We've tested it against a corn protein concentrate. All in all, we find that we have a benefit from using an alternative protein in the diet compared with a wide range of other alternative proteins. We tend to top out at a use rate of around about 15% inclusion in the diet. When we go higher than that, we get a slight reduction in performance, and we feel that we may be getting that as a result of the level of yeast products and the 24% yeast product that we've got in the 52% protein product, that we're actually getting a little bit too much yeast in the diet. And too much yeast in the diet will give an overstimulation of the immune response and tend to see a depression in performance. So up to a 15% inclusion rate, corn fermented protein can replace a range of different proteins in diets for aquaculture. We've had great success in 3 different trials with shrimp, where we've been able to improve the survivability in shrimp consistently as we have used corn fermented protein in the diet. At the end of the trials with Atlantic salmon, we looked at the gut morphology of the fish. Fish fed 10% corn fermented protein not only displayed normal distal morphology, but also improved intestinal conditions. The proportions of fish with moderate, score 2, or severe inflammation of the lamina propria, submucosa and serosa were all higher in fish fed the control diet compared with fish fed the 10% corn fermented protein. Therefore, there was strong evidence that we had an improved intestinal morphology when we were using corn fermented protein as a replacement, particularly in this instance, of soybean concentrates in the diet. The use of corn products in aquaculture tends to be associated with fillet discoloration. This is due to the carotenoids that comes through high levels of carotenoids in corn products. In the maximized stillage co-products process, the corn oil is recovered, and when we recover the corn oil, that recovers most of the carotenoids which are soluble in the oil. So we have only low levels of carotenoids in corn fermented protein. In several trials, we've looked at the impact on fillet quality and fillet coloration of using corn fermented protein in the diet. And without exception, we have not seen any impact of the carotenoids on fillet color when we've used corn fermented protein in the diet. So let's start and look to the future. One of the things that we've got in the fermentation process, and I've talked about it already, is the production of yeast. So could we start to design the yeast that we that we use as a fermentation yeast to also be a pre or postbiotic in our feed formulation. And that's one of the areas that we're now turning our attention to. The term postbiotic is given to a preparation of inanimate microorganisms and all their components that confer health benefits on the host. Well, we're suggesting we've got health benefits already in terms of intestinal morphology. So we believe that in the future we'll be able to design yeasts that will be actually termed postbiotics in our corn fermented protein product. Right at the start, I talked about the sustainability of corn and the production of corn to produce renewable fuels and a sustainable energy source. We've recently carried out calculations on the impact of using corn fermented protein compared with soybean alternatives and imported soybean meal into Europe, and the impact on greenhouse gases and the LCA value of the final produced feed. We looked at a range of trials that we carried out in salmon, turkey, broilers, and without exception, the replacement of soybean meal by corn fermented protein gave us a reduction in greenhouse gas production. That reduction was approximately 14% over the 3 trials that we have carried out and the formulations that we produced. So the use of corn fermented protein as a replacement of alternative proteins actually reduces the GHG value of the feed that we've produced. So let's bring this presentation to a close. Why should we use corn fermented protein from Green Plains? Well, I've tried to tell you that corn is a sustainable source of protein. We're turning corn from being a production of energy into a multi-purpose crop where we can produce energy and protein from corn. We produce a highly digestible, proven product for use in aquafeed. It's a consistent product. In feed trials, we've shown superior performance compared with other alternative proteins. We've shown improvements in intestinal health. The product is antibiotic free and it is commercially viable. It is produced in commercial quantities with resilience in the supply chain. So what's the future for grain biorefined feed products? We can start to use additional enzyme hydrolysis to increase the protein yield. And I showed you early on that we can move from 50 to a 60% protein product. We can use alternative feedstock grains to increase available protein. We've already shown that if we use wheat in the fermentation, which has a higher protein content, we've already shown that if we use wheat in the fermentation process, we can increase the protein content of the final product to over 60%. We're going to optimize the value of fermentation. Use that 60-hour fermentation to get the best out of the products that go into fermentation. If we put phytase in the fermentation, we can show we can significantly increase the phosphorus availability in the final product. We're going to use yeast as a vector of novel feed ingredients. And there's also the potential to use the fermented fibre as a benefit in the hindgut of monogastric species. So all in all, corn fermented protein makes corn into a multi-purpose energy plus protein product. And it has significant benefits for aquaculture in terms of producing sustainable feeds for aquaculture. Thank you very much indeed. You have my contact details in this final slide. If you require any further information, please do not hesitate to get in touch with me. Thank you and goodbye.